Welcome to the last week of our reinforcement learning course. Today we're going to finally tackle one issue we've been carefully avoiding and only covering at a minimal level in weeks 1 through 5 of the course, namely the exploration versus exploitation problem, as the title kindly suggests. We've already learned at least, three major ways of how you can build reinforcement learning algorithms. First, there were the black box methods like cross-entropy method, evolutionary strategies, or any other method that basically tries to take reinforcement learning problem for a gradientless optimization one, or something similar. We've already tackled at least two major algorithms in the so-called value-based reinforcement learning family, namely Q-learning, SARSA, value iteration, actually much more than those two I've suggested. We've learned how to approximate policies with neural networks, any other approximators, and we've finally learned how to perform direct optimization on a policy as a probability distribution in the previous week about acrocritic, reinforce, and similar ones. So all those algorithms have one common problem. They only learn by trying actions and seeing which of them work better. So if given Q-learning, you always pick the same action, you're never going to learn anything. So, of course, we've made up a few heuristics of how to speed up this process, like epsilon greedy exploration. And today we're gonna, study a few more heuristics, although much more efficient and much better studied theoretically. So, exploration versus exploitation. Welcome to this week. Now, the next thing we're gonna do is we're gonna simplify our problem a little bit, or quite a bit actually. Instead of tackling the usual market decision process we've been dealing with from like week 2 to week 5, this time we're only going to consider a single-step decision process, also known as multi-armed bandit. The difference here is that your agent only sees one first observation or state, he picks an action, he gets a feedback, and then the whole session is bound to terminate. The new session starts over, and the next observation agent sees in the new session is completely independent on his actions in the previous one. This is, of course, a grossly oversimplified view on any practical problem, but for starters, it is very useful sometimes where you have to cut the corners in your formalization. And besides, it's much simpler to describe advanced exploration methods in this setting. The formulas get much shorter. We'll, of course, get back to the multi-step decision process later in this week. But for now, and until midway through this section, consider everything we say about the one-step decision process. So as I have mentioned to you already, those one-step decision processes usually go by the name of multi-armed bandits. The story behind this name is quite simple and weird at the same time. The original multi-armed bandit is a situation like this. Imagine yourself in the middle of a gambling club actually, and before you stand 6 slot machines, like in this picture. Each of those slot machines have a different set of rules describing how do they pay you and how much money they take and what's the outcome, what's the distribution over the rewards they give you. And your objective is to find a slot machine which gives you highest expected reward. Of course, there might be some digressions from this formalism depending on what you want to achieve in this gaming club, but for now let's consider the expected reward problem. Of course, you could pick just one machine and stick to it because, God knows what all those other machines bring you. But a rational person, if he has a lot of money, could try to explore some of those machines, all of those machines first, get them a few tries, and only then converge to something that works better. So, of course, you're highly recommended not to apply this strategy to an actual gambling situation, because in any real casino, all those slot machines are going to be stacked against you. Otherwise, the owners of casino would get no profits. But in any real situation outside this gambling, it's often possible to reduce the problem to something similar to the multi-armed bandit. Now, imagine you are not trying to gamble, but instead you are solving an optimal banner ad placement problem. So you have a user, which is, in this case, mapped to a gaming club. And for this user, you have 10 potential banners, each of which he can either click or not click. In this case, if you show user a particular banner, this maps to you going to a particular slot machine and, inserting $1 in it and seeing what happens. $1 here is basically your time and electricity and all the opportunities you could have lost or could have gained. Then a user is either going to click, which is similar to a slot machine giving you a jackpot or whatever, or giving you some money, or not click, which is the same as, you wasting your money on the slot machine. And you have to find a policy of showing a particular user some set of banners so that it has the highest probability of clicking on them or bringing you a potential profit in the expectation, of course. So of course the multi-armed bandit formalism is rather limited. For one, it completely neglects the effect of agent's action on his next observation, which would be far from true if you tried to play Atari or make a self-driving car with this multi-armed bandit at core. But turns out a lot of other practical problems can still be solved by them with almost no loss. In this case, we've just gone through the banner ad example, where the state was the user you were trying to get to click on your ads. Your action was a pick of a particular ad, a particular banner to show this user, and the reward was the expected revenue, or just the revenue for this particular case where you've shown a user this banner. Basically, click-through rate modified by the multiplied by the amount of money you're paid for clicks. Aside from that, you could also try to solve the recommendation system problem. See your own online store where users buy stuff, and you also suggest them to buy more stuff that they might be also interested in. In this case, your state is also a user, or whatever entity buys stuff from you, maybe it's a robot, and the action is to recommend this user a particular item. In this case, what do you think the suitable version of feedback would be? Well, yes, if it's an online store where you would try to make as much money as possible, then it makes sense to measure feedback as basically the amount of profit you made from items you have sold if user has bought them. So again, you can simply compute this as an expectation. If it is a different thing, say a free site like YouTube, then you could consider instead to measure user satisfaction, users retention, or any other complicated words that measure how satisfied user is with your service. In case of again YouTube, this would be the fraction of users that liked your recommendation or that have watched the whole video from start to end. Okay, of course, in any practical situation you can come up with more efficient metrics, but this is not the subject of our present lecture, so let's go on. A few less obvious problems are the problem of, for example, information retrieval. This too can be solved by bandits. In this case, your state is user's query, and your action is to show user a particular set of search engine responses for this query. The feedback is whether user was satisfied with this search, whether he has found what he was looking for. And again, it is not that trivial to measure the user satisfaction without having them reported to you directly. Of course, these are all huge problems to tackle in one lecture, and let's just go on, basically.